Hi everyone, hope you're doing great. And I'm here to give a presentation on my implementation of NeRF, which is the Neural Radiance Fields. Essentially, it is a piece of technology which comes under deep learning, computer vision, and computer graphics and is used for 3D scene reconstruction. Basically, if you have a bunch of 2D images of a scene, then you can train an MLP or a neural network to learn the features of the scene. Then you can use the neural network for novel view synthesis or generate images of the scene from different camera positions of whose images you did not provide earlier. So this is my implementation, which is based on this PyTorch NeRF GitHub repository. So this is how the training code looks like. So initially we have the NeRF class, which forms a neural network. It contains all the layers, the activation functions, and the number of neurons in each layers, which is based on the implementation details provided in the original NeRF paper. Then we have the main function where the training actually takes place. Initially we have some configurations. Then we move on to loading the dataset and data pre-processing. The data pre-processing consists of converting the images, which is the ShapeNet car image dataset used in this implementation, and converting it into a 100 by 100 RGB pixel format. Then we set up a test view. It is a random image selected out of the dataset against which our model is compared to test its accuracy. Then we move on to the iteration stage, where in each iteration we train the neural network and optimize its loss. Let's look at some of the results. I've trained the model on the free Tesla T4 GPU provided by Google Colab. So this is actually a real image taken out of the dataset. This is how the input images look like. Once the training starts, this is how the NeRF prediction looks like. Initially it knows nothing. Then slowly and slowly it starts to learn the scene, and then we can see it starts to take the form of a car, and the iteration keeps on going for several thousands. And here we can see that the PSNR, which is the peak signal to noise ratio, keeps on increasing. So essentially PSNR is a really famous metric which compares the pixel wise difference of the real and the predicted image. So here basically if the PSNR is increasing, then it's good. So this iteration keeps on continuing for almost 8500 times, and compared to the original one runs for 300,000 iterations, but due to computational resources and time limitations, I have kept it in less than 10,000. So these are some of the novel views generated by the NeRF model. These are some more scenes which are generated by the model itself. Here the resolution, although it can be improved, but the fact that we are able to generate these scenes means that our model is working. These are some of the details of the nerf.py file where the training actually happens. These are some of the implementation details. Then future scope for this project includes Instant NGP. Instant NGP is a method given by NVIDIA which uses CUDA to reduce the training time of NeRF. Then another problem in NeRF was the slow inference time. So the images that you can see here, each of them took like 1.5 minutes to 2 minutes each. So this is not really very applicable or practical in real world applications. So mobile RTL is an interesting paper that actually tells you how to do real-time inference, that too in mobile devices such as your mobile phones. Finally, this is a repository, a GitHub repository for various NeRF papers, which contains great approaches and optimizations done in the original NeRF model to increase its applicability, and efficiency. Thank you.